Right, hello. I said I needed to look at probability in a bit more detail, and I'll be looking at problems like, we talked about tossing a coin. You got half a probability of getting a head is half, probability of getting a tails is a half, and so on. A more complex problem would involve something like you toss a coin twice. What's the probability of getting a head and a head? And I'm going to introduce this in a very hand-waving way and state that when the question says and, probability of a head and a head, when the question says and, then you multiply. Now, I mean, this might seem counterintuitive, but hopefully this sort of the counterintuitive aspect of it will help you to remember. And in the question implies that you multiply. So, what's the probability of a head and a head? Well, as I said before, I'll state the rule specifically. Probability of a head and a head equals the probability of a head multiplied by a head. So that's a half times a half equals a quarter. Okay. So you toss a coin twice, and the probability of getting two heads will be a quarter. Now, I've emphasised the use of the word and, so sometimes you might need to rejig the question. I could have said, toss a coin twice, what's the probability of getting two heads? So you need to rejig the question to say, okay, that probability of two heads is equal to probability of a head, and then proceed as before. So this is the, okay, I spread out on two lines, but that's the rule, okay? Now, I need to point out that this rule will probably always work at GCSE level, but to be more precise, this rule will work so long as the two events are independent. Now, by independence, I mean that the probabilities are not affected by the other event, okay? When I toss the coin the second time, the probabilities are still a half heads, half tails, okay? The probabilities have not been affected at all by this first event. Okay, so I toss the coin first, it's a half-half. I toss the coin a second time, still a half-half. The probabilities have been unaffected. The two events are not connected in any way. The one event will not affect the probabilities in the other event. So in that case, they are independent. And that's basically all there is to it, really. There's, you can say, okay, again, I haven't got a proper dice, but this is a poker dice. What's the probability of getting a jack? I throw it twice. What's the probability of getting a jack and a jack on this poker dice? Well, the probability initially is 1/6. Well, I'll state the rule again. Probability of a jack multiplied by the probability of a jack. Okay, so that's the again, that's the basic rule, so long as this situation is independent. The probability of getting a jack is a 1/6 multiplied by the probability of getting a jack on the second throw. There's your jack there, okay? That's equals to 1/36. And if I had a sort of proper dice, for want of a better word, with ones and twos and so on, I could say, okay, what's the probability? Throw a dice twice. What's the probability of getting two sixes? Well, it's the same thing. The probability of getting a 6 would be 1/6, and it's so that's the same thing. So a probability of a 6 on the first throw, and a probability of 6 on the second throw is given by this, the same probability. But it could have a different scenario. I could have two dice and throw them simultaneously, and that would be exactly the same problem. Two dice, throw them simultaneously. What's the probability of both of them being 6? It would be exactly the same calculation. I can mix them up and say, okay, what's the probability of getting a head and 2 on a pack of cards? Okay. So I'm going to toss a coin and take a card from a pack. So what's the probability of so that's our rule again, probability of a head multiplied by probability of a 2 in a pack of cards. So that's equal. Probability of a head is always a half. the card I draw from the pack is unaffected by what I've thrown on the dice, and so okay, I've got a 2 on the top. You know, it's a case of drawing a card from this pack. What's the probability of getting a 2? Well, that's 4 over 52, which, if you can remember what I said before, that's also equal to 1 over 13. So I'll just do that straight away. So that's 1 over 26. So I can mix probabilities like that. Okay. Now, as I said before, I've stated the fact that that rule only works when they're independent. The events are independent. So I think in practice at GCSE level, all calculations you're required to do will be independent. So you don't really need to worry too much per se. But you do need to understand what independence means. For example, you could have a situation where, I don't know, probability of person. You got two people. Probability of person A being late for work is a quarter, and probability of person B being late for work is a quarter. Probability of A and both late, shall we say? Okay, so that's the separate probabilities. But the probabilities that on a particular day A and B will both be late is a third. Now, I mean, this could be a typical GCSE question. You could then say, is this scenario independent? Well, remember what I've said. The rule, take a look at this. For independence, the probability of A and B both late. Okay. Remember what I said. For that to be independent, you're going to have probability A late multiplied by the probability of B late. Okay. If the situation is independent, then that rule works. So what do I get? Well, I've got probability of A is a quarter, probability of B late is a quarter, so that's 1 over 16. So if this is an independent scenario, if these two events, A late and B late, are independent, then the probability that they will both be late on the same day is 1 over 16. But actually the probability that the actual probability that they're both late on the same day is a third. So this situation is not independent. And you can think of plenty of scenarios for this. I mean, it could be that A and B come in on the same train line. So if person A rings in and says, okay, he's delayed because there's problems with the trains, then the probability of B being late is then affected. Okay, you can see what I'm saying there. That probability if A is late, then the probability of B being late is affected. It could turn out later on that B comes in on time, but the actual probability, as soon as A rings in, the actual probability that B is going to be late will be altered. So there's a direct connection between the two. You know, obviously vice versa. If B rings in late, then the probability that A is going to be late is altered as well. So that's a good scenario of a situation which is not independent. So you need to remember the rules anyway. If the situation is independent, then this rule works. But if not, it doesn't. So that's your situation if it's independent. It differs from the real life situation. So this situation is not independent, as I've stated. Now, the other scenario you'll need to come across is something like with a pack of cards. You say, okay, pick a card from a pack, and what's the probability of getting a... I'm getting ahead of myself here. I pick a card from a pack. What's the probability that the card I've picked is either a 2 or a 3? Well, the rule here is that you add them. Now, as I said before, the probability that you get a 2 is a 13th, I should say, 1 over 13, and that's 1 over 13. So that's 2 over 13. Okay, so you've got this logic here that if the question says and, you multiply, and if it says or, you add. Okay, so that's slightly illogical to possibly, but there's within mathematics, it's not too illogical actually. There is a branch of mathematics called Boolean algebra, where this expresses the rules. You know, if there's an add, you multiply, and if it's an or, you add. And within electronics, there are particular gates which are commonly used in computers. There's an AND gate and an OR gate, a transistor logic circuits, and and an AND gate will multiply the signals that come into it, and an OR gate will add signals. So this is, it might seem illogical at this stage. Maybe the first time you've come across this logic, but it's not particularly unusual. Now, the one thing you need to note about this is that there is a condition analogous to the previous condition. The previous condition was that you had this formula that worked when the two events were independent. Here, this is going to work just so long as the situation is mutually exclusive. Okay, and again, I think in GCSE most calculations will be mutually exclusive, so you don't really need to what shall I say? I'm not encouraging you not to learn it. You need to know what it would be helpful to know what mutually exclusive is, but you probably won't necessarily need to use it in any calculations at GCSE level. And what mutually exclusive means is that for any particular event can only satisfy one of these conditions. Okay. An obvious counterexample would be to say, I pick a card from a pack. What's the probability that it's 2 or probability that it's red? Okay. So I pick a card from a pack. Well, I've got this very handily, this card here. I pick a card. I get this, and this fulfills both those conditions. That's a 2, and it's also a red. So that means that I cannot use this. This is not mutually exclusive. So I cannot use this formula. Okay. In order to use this formula, you've got to have a situation where these conditions can only be satisfied in a particular event. This can only, a particular event you can only satisfy that or that, but not both together. That's the condition you need to apply this equation. Right. So I'll call an end to this particular video, but I need to go on to this even further because I've been a bit loose in what I've said previously. I've been deliberately picking my scenarios here. So probabilities of a head and a head. Okay, that's okay. But if I said, well, I won't write it down. But if I said, okay, I toss a coin twice, what's the probability that on the first throw I get a head, and on the second throw I get a tails? Well, that'll be the probability of a head on the first throw multiplied by the probability of tails on the second, and that'll just be the same numbers. It'll be a half times a half equals a quarter. But if I was to ask another question, when I say this is a totally different question, and say, I toss a coin twice, what is the probability that I'm going to get a head or a tail? Now this is a different scenario because there's actually two scenarios that would fulfill that question. I could get a head on the first throw and a tail on the second, or a tail on the first and a head on the second. So actually that's a bit more complicated. So if I say, okay, I might be sort of stressing this a bit too much, but this is important. If I say probability of a head on the first throw and a tail on the second throw, I can do that using this formula. But if I just say loosely, toss a coin twice, what's the probability I'm going to get a head or a tail? Oh, sorry, a head and a tail. That is more complicated. I need to look at that more in more detail. So I'll do that in the next video. Thanks for now.